I just washed my hair, but it doesn't matter. I'm on my way to master machine learning, and there's still one very popular and important neural network that long stood unconquered by me. I'm talking about diffusion models that start from pure noise and generate images, videos, text, and even protein structures. I want to learn how it works, and so do you, but it's not gonna be a normal video, and not only because I have a towel on my head, but because I don't want to just scratch the surface. I want to scratch until I get to the bottom of this thing. Why? Because I have to understand the world, you see? We're going to study the problem statement, first solutions, why diffusion works so well, the background. We're gonna study the papers, the math behind them, and the code for it, and the whole stack. What do you say? There's so much to talk about, I'm going to explode. You know the famous bottomless pit? This is it. We just dig and dig and dig, and it never ends. We dig forever. Where do I see myself in 5 years? Digging. That's what I said in the interview once, and I did not pass it. I still wonder why. Doesn't matter. What matters is that for the past few months, as I was studying for this video, I felt like I start to get it. Like I start to uncover the true nature of machine learning. And my goal today is for you to get it as well. You'll see. Enjoy. Welcome to the image space. Just don't look up to not get overwhelmed. Alright, forget it. And still, a 1000 by 1000 pixels image has a million dimensions. Here we only visualize 2 plus height corresponding to the image quality, or probability, if we treat it as the quality data distribution. As we can see, most combinations of pixels are terrible, since a random point in this space corresponds to a random image, which is most likely noise. We can also notice that our landscape is spiky, because when we finally get a good image, almost any deviation from it is worse. And even if we take two good similar pictures, a midpoint between them is either a blurry mess or awful nonsense. This space is our challenge for today because this is the ground truth that we don't know about. We can't practically evaluate each combination of pixels, even if we had some magic evaluation function. And that's the first step, like how do we even tell what is a good image? In humans we call it having taste. In neural networks we don't call it, it doesn't exist. So without using human judgment or immature techniques that I would like to explore one day, like open-ended search, novel masterpieces are out of our reach. In fact, without a way to evaluate images, everything is out of our reach. What we can do, however, is show our model example target images so it will find patterns and recognize where the good images are in this space. That's the best we can do for now. So how do we train it? Here's an idea for you, and it's a great idea. Make a model that outputs an image, either from nothing or noise or some prompt embedding, just whatever it needs. Make it output an image, compare it with what you want it to get, and congratulations, you have an image generator that's almost instant. We don't need the whole iteration nonsense. Or do we? Where's the catch? Let's test this idea on a dataset of handwritten digits, and we get... Not quite. Sadly, because that would be a breakthrough. But it's an informative fail because it looks like our model learned to output our target images simultaneously. It just gets confused, probably trying to minimize the distance of its output to all our target images. So let's condition it on a specific digit, like a 0. Alright, so where's the catch? Here's a well-informed machine learning advice for you. If your model works, remain skeptical. Don't let this innocent-looking 0 fool you. It has blurry edges because it's the average of many zeros in our dataset, and it's just pure luck that all the zeros are roughly in the same spot in our dataset. So if you average them out, it's still recognizable. This approach barely works here, but for any more complex dataset, it won't work at all. For example, right now you're looking at the image of an airplane, if you didn't realize, because averaging many airplanes at different angles and positions is nonsense. This is a core problem because we need something else entirely. We need a paradigm shift because minimizing the distance to our targets won't work. While sampling a digit, we're landing in the middle of all the digits that could be sampled. That mathematically satisfies our model, like fulfills our objective, but it doesn't satisfy us. Remember this: if we minimize the distance to our targets and there are multiple valid targets for a given input, the model will learn to output the average of these valid targets. This is very important. For image classification, for example, this is fine. Maybe your digit classification model output is half-half between 1 and a 7. And it's probably because it's hard to tell if it's a 1 or a 7. This output makes sense, it's still informative. But for generating images, we don't want the average of multiple images because that's nonsense. That won't work. So scientists had to get creative to overcome these hardships. And the first real solution came with GANs, generative adversarial networks, where generator produces images indistinguishable from the real ones, and the discriminator tries to call out these fakes. So the generator tries to get better at fooling the discriminator, which results in images that look increasingly real, and the discriminator tries to get better at spotting fakes, posing an increasing challenge to the generator. It's a paradigm shift that we needed because we're no longer minimizing the distance to our targets. We optimize for realisticness. That's a word. We optimize for indistinguishableness from our dataset. That's something else entirely, even though it sounds kind of similar. But our model, instead of thinking, how do I match the dataset? How do I match the dataset? Is thinking, what makes the image real? What makes the image real? What makes the image real? And that is very clever. But it turns out that discrimination is not that great after all, surprisingly. The whole idea of competing neural networks is very fragile because it requires synchronized interplay between the two networks, and none of them can really deviate from each other. If your opponent is too strong, then most of the things that you try fail, and it's hard to learn from that. And if your opponent is too weak, then almost everything you try succeeds and you win too much. It's hard to learn from that. The challenge must be just right. This is a problem on top of neural networks already being unstable by default. For example, ever heard of one pixel attack? It sometimes takes a single pixel to throw image classifier off and suddenly consider panda an airplane. That can be explained with the fractured entangled representation hypothesis that shows that underlying structure of these networks is a complete mess, which makes them behave uncontrollably in unusual cases. All I need you to remember is that they put unstable neural networks in an unstable environment, and even if they worked, they struggled with creativity because the generator could abuse just a few reliable ways to fool the discriminator. I saw a tweet recently that said, I really cannot believe that GANs are a thing which actually exists that people actually train. Yeah, it was a miracle that any of this worked. But GANs had their successes, we have to give them that. 2017, 18, 19, 20, 21, they were the best image generators that we had. They were also the first ones to scare the media that the era of deepfakes is coming, because we could generate realistic faces of people. You know this person does not exist.com? That's GANs. One day I might dive into details and play with them, but for now we have to go further. Let's change the angle now. GANs worked alright, but we're back to the original problem, bringing us back to first principles. Let's say we have a model that's trained to generate one missing pixel, like this one here. this model would perform flawlessly. Yes, it outputs the average of possible options here, but the space of possible options is very small because the pixel has to match the surrounding pixels. There's a lot of information to ground it and constrain it. That's how we get to dive into autoregression, because there's potential here. I feel like this wasn't clear enough when I was recording the video, that there's potential in generating one pixel at a time. That's why we get to dive into autoregression, right? It makes sense, even though it doesn't always look like it. Autoregression is when the model iteratively uses its past outputs to produce future outputs. It's best understood with an example, like ChatGPT. You don't get an output immediately. ChatGPT looks at the context, generates the first word, and then repeats, meaning looks at the context that now includes the first word and generates the second word, and so on and so on and so on. That's autoregression, using your own outputs to produce an output. And notice what's happening here. Autoregressive models converge on an output in some sense. At least for things like ChatGPT that operate on finite sequences, right? Because the space of possible outputs gets smaller and smaller and smaller because the context grows. There's more things to constrain us. ChatGPT looks at the whole context, produces the first word that has quite a lot of options probably, but then the second word has much fewer options because it has to match the first word and the whole context again. Right? Then the third word has to fit two previous words and the context. And the sentence has to make sense, so the number of options gets smaller. That's how we arrive at a legitimately good idea this time. I mean, it comes with its own problems that are quite obvious, but there are no hidden tricks this time. How about we generate images pixel by pixel? First pixel will likely be an average of many options, but it's just one pixel, so we're not getting a blurry image yet. Then the next pixel is not the average of tons of options, but the average of all the pixels that make sense being next to the previous pixel. Then the third pixel, and so on. And bit by bit we generate decent images. Painfully slowly, but it's something, right? It's a step in the right direction. That's how we get to understand the problem, the solutions, and the world. We just kind of explore our way. So now I have an idea for you. We all love my ideas. How about instead of generating pixel by pixel, we generate the whole image at a time? Okay, then we're back to the original problem of generating the whole image and it's blurry. It's a blurry mess of all target images. Okay, that's fair. But now what if we take an in-between scenario between the two extremes? Let's say we will generate 4x4 patches of pixels. It's a speed up of 16 times in generation, but the image quality drops because there are more options for the patch. The patch is less constrained because the distance between patches increases compared to pixel, and we also generate pixels and their surroundings at the same time. And the pixels depend on their surroundings, but we don't know the surroundings because we generate them at the same time. So yeah, you see how it works. We have a trade-off here. We sacrifice speed for quality. If the model knows the surrounding pixels, it can perfectly fit the pixel in. But if we generate the surrounding pixels and the pixel kind of at the same time, then the image gets blurry because there are many viable options. That is why generating patches of pixels is the worst way to do it, because the neighboring pixels are the most correlated to each other. We should generate pixels that are far apart as possible. Think of it like this. Is it easier for you to complete the image with these 16 pixels missing or these? That's our trick to generate 16 pixels at the same time without sacrificing that much quality as if we had done it in the patches of 16, since each pixel is constrained by its surroundings. So we want to generate pixels in the most spread out way possible. But you know what's better than generating 16 random pixels? Generating 32 halves of pixels. It's like we generated the same amount of information, it's just even more spread out because it's spread out across 32 pixels now. You know what's even better? Generating 64 quarters of pixels. Like it would take 4 iterations to generate full 64 pixels. That's how we arrive at generating a fraction of each pixel iteratively. That way we slowly converge on a clear image. It's like we don't have to make irreversible changes before we figure out what's the idea for our image. We have like rough outlines at the beginning which constrain us, and we slowly move to details, which is what we observe in diffusion. But we're not at diffusion yet. For now we know only that we generate a fraction of each pixel at a time, iteratively. That's fine, but we have two problems. First is creativity, because we start from the same point in the image space every time. So like the trajectory in the image space is so similar that we will struggle with creativity. And the second, the bigger problem even, is that we lack guidance. We cannot guide our model along the rollout, along the trajectory. We can only judge its final point. And these two problems are brilliantly solved by diffusion. I will explain what it is exactly in a second, but just to give you a rough idea of like how it works and why it's so good, is that we start from noise every time, and the noise is different every time. I mean, it's similar because it's like it has zero information, it's just pure noise, but the point in the image space is like different every time. It's almost impossible to start 2 times from the same point. So we force the neural network to generalize, to get a feel, get an intuition about how to navigate the image landscape, because it will have to get to the same point from a ton of different points. So that's nice, and also no trajectory will be the same pretty much twice, because the image space is so vast. So that's creativity roughly solved. But most importantly, diffusion enables us to guide our model along the way, along the trajectory, which is, I'll give you some background because this is a very real and huge problem in large language models. Maybe you know that one of their final stages of training is reinforcement learning fine-tuning. And it's very problematic because, I mean, first of all, the fine-tuning works only on concrete examples where there's a concrete answer, correct answer. So we make a rollout, the model produces a ton of tokens. For hard problems, it's a lot of tokens. And we compare its output to the real answer. And if it's correct, we increase the probability of all these tokens. And if it's wrong, then we decrease the probability. That's fine. But there's a problem. Like, there are many problems with this. First of all, if the model never gets a good answer, there is no signal. Like, we cannot tell them that, okay, you didn't get a good answer, but this was correct, so you should keep doing this, or this was nice. There's no way of telling that. And maybe it gets the correct answer, but for the wrong reasons. Just by pure luck, even though it made no, like the whole process made no sense, but the answer is right by pure chance, right? And what happens then? We increase the probability of all these mistakes. Or maybe it was correct for the correct reasons, but still made some mistakes along the way. They were not catastrophic because he still got a good answer, but we increase the probability of these mistakes. And this process is just widely problematic. It's been shown that if the model is fine-tuned on math, let's say, it really gets better at math, but it deteriorates in pretty much all other aspects, which is just it's just terrible. They try to use a separate neural network that will judge the model along the way, but all these setups are gameable. I've seen examples of the model outputting one letter, the same letter constantly, and the judge neural network is just copying. It's like wonderful answer, wonderful answer. But of course it's garbage because neural networks are messy, they're gameable, they cause endless problems, but not for us. Because thanks to modeling the generation process on diffusion, or reversing the diffusion, we solve all of these problems and we know exactly what the model should be doing at every step. Let's finally explain what diffusion is. Diffusion in science is a random drift of particles in all directions due to particle collisions until an equilibrium is reached. This is a part of a general principle in science that nature dislikes energy imbalances and everything tends toward an equilibrium. If you touch cold and hot things together, their temperatures will eventually match, making things more equal. Entropy only increases, things become more equal, and eventually we end up in the heat death of the universe where everything is so uniform that nothing can ever happen. And if there are kids listening, I was just joking. I mean, we're gonna be fine as long as you don't eat sweets and study hard. So diffusion is a real phenomenon that is easy to work with and easy to model and simulate because all we have to do is add noise. In the case of particles, you move them in random direction until you destroy all the information about their initial position. And with images, you add noise to them, destroying information in the most spread out way possible until no information is left. Mathematically, diffusion destroys any data distribution we had. In one-dimensional distribution, this forward process transforms any complexity into a Gaussian curve. In 2 dimensions, like a simplified image space, it would transform our distribution of good images into a multivariate Gaussian, and so on. And we learn to reverse this process with a neural network that fixes all of our previous problems. We balance generation speed and quality through iteration on all pixels at the same time, slowly converging onto a target image. This progression of constraints also prevents blurry images. By starting from noise, no trajectory is ever the same, increasing the model's creativity. And by modeling the generation as denoising, we can guide our model exactly through the whole process. And a quick remark regarding the guiding, that we will not be predicting the noise added at each step. We will predict the total noise added because the noise at each time step is random and it's wasteful to model that. The real signal is finding the starting point of this diffusion process. So we start here, perfect image, we diffuse it randomly, and in a messy way, and we just try to get to the starting point. We'll not be trying to trace out the whole process because that's wasteful, okay? So we talk about reversing the diffusion, but we'll not be tracing out the diffusion, right? We'll just like reverse the effects of diffusion. These were the main ideas behind diffusion because I care about understanding, I care about the whys and knowing how it all came to be. But it's all fun and games until it's time to get technical, because we would also like to know how to implement these ideas in practice, right? And I will do my best, but I will need you to focus because it wasn't easy for me at all when I was learning that. The groundwork for mathematically modeling the diffusion has been laid out a long time ago. I had a paper saved even, here from 2015, Deep Unsupervised Learning Using Non-Equilibrium Thermodynamics. It sounds serious, but I didn't study it after all because I didn't find it that crucial, because the first paper that showed how high quality images we can get from this system is this paper. That's why it's more interesting paper in my opinion, the Noising Diffusion Probabilistic Models from 2020. And 2 years after this came out, we had the whole like AI image revolution with stable diffusion, with Midjourney taking over the internet and everything. So this is the paper that started it all in some sense. So let's take a look because it's not an easy paper. We present high quality image synthesis results using diffusion probabilistic models, a class of latent variable models inspired by considerations from non-equilibrium thermodynamics. Alright, All right, very nice. They're doing image synthesis, and we'll have to do paper synthesis because like it's not gonna be easy. So uh, they assume that you have a lot of background knowledge, right? But even if they're mentioning some like certain keywords that you would have to know and Google, like Langevin dynamics here, I still feel like the language is unnecessarily complex in a certain way. But that's fine because we like a challenge. Also, this is what research requires from us. Because the greatest skill in research is being a nosy bitch that wants to find out. And we want to find out. We need to look at the abstract and be like, what is going on here exactly? What is a latent variable model? What is Langevin dynamics? What is going on here? You have to be so nosy that people say, it's none of your business, but it is my business. I need to find out everything about this abstract. But luckily for us, I made it all easier for us because I rewrote the whole thing because I didn't like it. I mean, no disrespect, it is well written for academics people, but I want to adapt it to a wider audience. So let's switch monitors, and we have my version, the noising diffusion probabilistic models. We present image generation using diffusion models inspired by ideas from non-equilibrium thermodynamics. Alright, that's fine. So it's obviously inspired by physical diffusion, and we'll be doing image generation, diffusion models, everything's clear. Our best results are obtained by approximating the true intractable loss with the weighted variational bound, designed according to a novel connection between diffusion models and the noising score matching using Langevin dynamics. Alright, it's obviously a complex sentence, but at least we roughly know what's going on. First, we know that we cannot calculate the true loss, so we have to approximate it with a weighted variational bound. And not everyone knows what it is, but now you have like a keyword that you can Google, that you know, it's good for academics and good for newcomers, that at least we know why are we even using this technique. And I'll be explaining it obviously later on. For now, it's enough that we know that this is a technique we use to approximate something. It's an analytical approximation method. And then they say that they made a novel connection between diffusion models and the noising score matching using Langevin dynamics. Obviously, there are more keywords to search up here, but I can tell you right away that Langevin dynamics is an amazing algorithm that makes the whole idea of these diffusion models work here. More or less, right? There are more improvements later on, but Langevin dynamics is an algorithm that enables us to sample from a distribution, from an unknown distribution, right? The image space that I showed you earlier is the true image space that we don't know about, and we want to sample from it, but we don't know it. So thanks to Langevin dynamics, we can sample from it by knowing the gradients only. The gradients of this distribution. There's a great video that I watched that explains this, so you can investigate further, but we'll connect later on. Like when we'll be talking about sampling algorithm, I'll mention that this is Langevin dynamics. Like we just follow the gradient and add noise to our direction. That's pretty much it, like iteratively. Okay. Our approach can be thought of as a generalization of autoregression since we iteratively converge on a clear image through progressive lossy decompression. So this is the autoregression that I mentioned earlier. So if you watched it, you know pretty much everything you know, you need to know. But also, obviously, you can think of the whole process as lossy decompression because we create a lot of detail from very little information, pretty much just our model weights. So that's something they want to mention, that's fine. Then on the CIFAR 10 dataset, or CIFAR, I don't know. It's like, I never pronounce this stuff, I never talk to anyone about this stuff, so I don't know how to truly pronounce that. I remember I was talking to a guy about arcsif.org, this page here, arcsif. And he was like, it's called archive, okay? It's archive. It's some Greek letter. Okay, archive. So I'm kind of detached from the community. I don't know how to pronounce stuff, but it doesn't matter. This data set, they got this score and this score here and something something. Like this stuff means almost nothing to me, but I guess it was useful for academics in 2020 to quickly judge how good the technique is, which is nice. And they also include the code, which is also nice. And now we get to the introduction that I also rewrote for whatever reason. So it's just a longer version of the abstract, but it gives us more background knowledge to see what's happening. But all right, deep generative models like generative adversarial networks, autoregressive models, flows, and variational autoencoders that you maybe know from my Dreamer video have recently shown the ability to produce high quality samples of various types of data. There also have been remarkable advances in energy-based modeling and score matching that have produced images comparable to those of GANs, which are considered in the year 2020 the state of the art. So this is my addition because it's not obvious. Like they wrote just this, and it's important to know that GANs were the state of the art. Like this is why they compare it to GANs, right? So it's nice that they give you the state of the industry, like just some background information. Then, this paper presents progress in diffusion models that are trained to match the original data by reversing a diffusion process that is a Markov chain that gradually adds noise to the data until signal is destroyed. And Markov chain is a process. It's a chain of events that only depend on the previous event. Meaning that when we're in the present, the knowledge about the present is everything we need to know to predict or make an action right now and predict the future and stuff like this, meaning that the past doesn't really matter. For example, you can think of tic-tac-toe, because in tic-tac-toe, the past, like when you see the state of the board, the past doesn't matter. The order of how the moves were played, it doesn't matter. Like the present is everything you need to know to make a decision or to predict the future or whatever. Like you have all the information just from the present. And using Markov chain here and like modeling diffusion as Markov chain vastly simplifies our problem and has like Markov chains have very useful properties, but you'll see later. It doesn't matter. I'm just like giving you some information. The models themselves are parameterized Markov chains trained using variational inference, which is an analytical method for approximating complex distributions, which is what I mentioned earlier, right? This is possible because when diffusion consists of small amounts of Gaussian noise, it is sufficient to model the reverse diffusion process transitions as conditional Gaussians too, making it a much simpler task for a neural network. This is a nice background information. They say that if we model the whole process as adding small enough amounts of Gaussian noise, meaning that we don't make huge jumps, but we make tiny steps, then we can model the reverse process also as a simple Gaussian, which is very simple to model with a neural network. At least much simpler than having some more complex, processes. That's fine. That's very nice. Diffusion models are straightforward to define and efficient to train, but to the best of our knowledge, there has been no demonstration that they are capable of generating high-quality samples. We show that this is possible, sometimes even surpassing the quality of published samples from other types of generative models. That's nice. That's one of the main contributions of this paper. In addition, we show that a certain parameterization of diffusion models reveals an equivalence with the noise and score matching over multiple noise levels during training and with annual Langevin dynamics during sampling. We obtained our best sample quality results using this parameterization, so we consider this equivalence to be one of our primary contributions. Okay, so apparently they're very happy that they showed that their process is equivalent to Langevin dynamics during sampling and to the noise and score matching during training, whatever that is. I actually didn't dive deep into score matching. It's fine. Despite their sample quality, our models do not have competitive log likelihoods compared to other likelihood-based models. One explanation we found is that the most capacity of our model end up describing imperceptible image details. So they give a reason why the log likelihood is not that high. We present a more refined analysis of this phenomenon in the language of lossy compression, and we show that diffusion models inference is a type of progressive decoding that resembles autoregressive decoding, but with the more general information generation order, which is what I mentioned earlier when I was talking about autoregression. So that's very nice. So we have all the background that we need. But this was my version. But in the actual paper, they also show you let me see, this diagram, which is an amazing diagram. My goodness. Let's talk about it. So this is a diagram that shows forward and reverse diffusion. Okay? And reverse diffusion goes to the right and forward diffusion goes to the left. When I saw this, I was like, nah, you cannot be serious. So obviously I had to make my own graph because I feel like they really underestimate how important it is to have a clear vocab that is not confusing for learning. So I have my own graph where forward diffusion goes forward and reverse diffusion goes in reverse. Absolutely brilliant. So with these graphs, we'll be slowly introducing the vocabulary and the math notation here. So like before we get into math in the paper, I'll get you through the math in my own version here. So this is our most basic graph that shows that we go from x0 in the forward diffusion to x capital T, where this index indicates time step. So a higher number means we're later in the diffusion process. So x0 would be our image with no noise, and xt would be our image that is fully noised, an image with no signal, just pure noise. Okay, and we have two processes. We have q and we have p theta. Q transforms the previous time step to the next, and p theta goes in reverse. And theta will mean that, like, theta are our network parameters. So this indicates that we'll be reversing this time step with our neural network. I hope it's clear so far. Now we go further. Don't look to the sides for now. For now, focus in the middle. That I wanted to make it clear that even though we noise the image and then denoise it, it's not really like this. It's not really like we trace out the process that happened. We kind of go back in time, but with a different route. So it's important for us to not confuse this x0 and this x0, because these are completely different things. So time goes in this direction and we noise the image, it's noisy, and then we reverse it, but this route is completely different, completely. So I wrote down some vocab here to make our later job much easier, to not leave any room for misinterpretation. So our Q is our forward diffusion distribution. But you can also think of it, so it's a distribution. It shows like how probable are next steps if we sample from it. But you can also think of it as a function, like here. I mean, it is like this, what it means. This is the distribution of xt's based on previous time step. but it's a distribution, but it's also like a transitional function, so to speak, because when we sample from the distribution, we get the next value, right? And the same for p. So these are distributions, but you can also think of them like functions. Like you'll see, hopefully it'll clarify if we use them in practice. And p theta is reverse diffusion distribution according to a neural network with parameters theta. That's what it means. And then this, like the difference between these two is very crucial for you to understand. So q of x0, I was very confused by it at the beginning. It's a distribution of x zeros, so starting points, distribution of starting points of forward diffusion. So it might look confusing, but when I phrase it like this, I hope everything is very clear, that this is our data set. Like, even though Q is the noising function and our data set is denoised, it has no noise in it, but this is distribution of starting points of forward diffusion, okay? And equivalently, this is not starting point of reverse diffusion. This is the end point of reverse diffusion. So distribution of endpoints of reverse diffusion, that is the distribution of generated images. So it's the distribution of our denoised images, the images produced by our model. And I wrote this here, that this is our data set. This is x0 distributed, that's what it means, distributed according to the distribution Q of x0, which is just our data set. This is our data set. And this is x0 distributed according to p theta of x0, which is our generated images. This x0 is not equal to this x0. I want to make it very, very clear. Now, the endpoint of forward diffusion and the starting point of reverse diffusion is actually the same thing. It's actually the same thing because it's just normal distribution, pure noise. So this is endpoint of forward diffusion and starting point of reverse diffusion, and these are both equal to normal distributions of pure noise with zero mean and identity matrix as the variance. I'll explain it in a second, but I was confused by this as well, because like, why do they specify the output constantly? And I believe they specify the output to not have to specify dimensions of 0 and I. I think so, because they could not write this and everything would still be clear, but it's fine. So this 0, because it's bold, maybe you noticed it's bold, this means that this is not a scalar. This is not a scalar, this is not a scalar. It's multiple values. And this means that this is a vector of zeros that has the same dimensionality as our data. So it's just like a 0 for each pixel. The mean is 0, and we signify it by mu. This is mean, which is just, it will disappear, so it's fine. It's just 0, 0, 0, 0 until our dimensionality. And this I, as I said, is our covariance matrix, which we signify by capital sigma. And our covariance matrix is identity matrix, which means that it has, ones on the diagonal and zeros everywhere else, and so on and so on, which just means that the variance of each dimension is 1, and our covariance matrix also specifies correlation between each dimension. So because we have numbers only on the diagonal and zeros everywhere else, it means that every dimension is fully independent. There is no structure whatsoever. It's just pure noise. That's why it's pure noise, because of the identity matrix and 0 here. And the last thing that's left in this graph is that this distribution of generated images is defined as the following. It's defined, this sign means defined as, so this is defined as an integral over the joint distribution of all the time steps with respect to all the latents. So, I mean, you have to know exactly what it means. Like, this process is called marginalization over the latent variables. If you want to read more, it doesn't really matter. All you have to know is that to figure out what's the probability of generating each possible image, like there's a ton of them, but this is the true distribution. So to figure out what images are even possible for us to generate for our model, to figure out the true distribution of our generatable images, we would have to calculate the integral. I mean, we would have to sum up the probabilities of each possible trajectory that we could ever take. And knowing how vast the image space is, you like intuitively know that this is just like good luck in calculating this. It's not possible. Not possible. That's why we'll have to use approximations. Now we have our third version of the diagram where we dive into details of each process. So, first of all, when we're talking about forward diffusion, they'll be calling it in the paper forward process or diffusion process. And they give you a choice to use. They're just like, yeah, just use whatever. And that introduces complexity. And we don't like unnecessary, like, we're fine with complexity. We like a challenge, but we don't like unnecessary complexity. Because why make it complex? So forward process is unclear because what process? Like, process of what? Like, we know it's diffusion from the context, but why not make it explicit and very clear what we're talking about? And diffusion process is like borderline pleonasm, which is just using unnecessary amount of words, like advancing forward. It's like advancing is forward, you don't have to say it. Or like a month of April. April is a month, you don't have to say it. So I don't like this because diffusion is a process, diffusion process, and they give you these two options. And I just call it forward diffusion. Forward diffusion. There's no ambiguity. It's forward diffusion. Thank you for your attention. So forward diffusion is a process that from unnoised image generates all the noisy versions of the image, and this distribution is a product of all the intermediate distributions, of all the transitions, where each transition is defined as a normal distribution where to produce a noisier image, we take less noisy image, we slightly scale it down, I'll explain this in a second, and add slight variance to it. We add a noise of this scale. While this is beta t, it's defined by our schedule. So we will call this variance schedule or just betas that defines how much noise we add at each step. It's very important. It's like a noise scale coefficient, but a collection of them. And just to give you a rough idea, this is 0.0001 and this is 0.02. And they just linearly interpolate between these two values. So a graph of our beta value over time is just like this. Okay, just to give you a rough idea. So it's like small amounts of noise and more over time. And that's why this is our noise scale that's added. And we also slightly scale down the mean of our previous image, because this is slightly less than 1. Okay, and they could use a separate parameter here, but for convenience and with experimentation, they were just like, oh, it doesn't matter that much, we just set it to square root of 1 minus beta, just to have one parameter. So there's not much justification for using this parameter exactly, but there's justification for scaling this mean down. Because if we didn't do that, the variance of our image would just explode. Meaning that we would not have pure nice Gaussian noise, we would have extreme values that are all over the place. I feel like I under-explained this because, of course, when we have some distribution and we add noise, like we end up with long tails, which end up escaping our bounds of our pixel values. So they get squished back in and we have like a lot of extreme values, but also a lot of noise in the middle. But for it to be a proper noise distribution, a pure Gaussian, of course we have to scale down the mean because we want to end up with zero mean at the end. So we have to destroy any information about the mean that we had. So of course we have to scale it down. So that was our forward diffusion, and I realized I missed 2 dots here. It doesn't matter. And now our reverse diffusion, p theta, that samples x capital T fully noised image and produces up to x0, and is defined as the probability of sampling this specific noise and multiplied by probability of each transition. Maybe you notice that we have this additional term here as compared to the forward diffusion, because here, like the x0 was given to us. It's not sampled really. There's no probability here, it's just like given. So the probability of it is 100%. So we don't have it here. And then our reverse diffusion transition is defined as a Gaussian, a normal distribution that produces less noisy image with mean that comes from the network, right? We have the theta, we have this produced by the network, and variance produced by the network as well. I mean, they write it like this to give you like a general overview, but later you see that the variance will be set and calculated. Like our neural network will not produce it, so we can only focus on the mean, but it's fine. And now we're in a great position to come back to the paper, because I want you to get a feel, get an intuition about how these papers are written and constructed. Like, we know all this, I explained it to you already, but I want you to go to the paper as well. So let's do it. Diffusion models are latent variable models. Okay, I didn't explain it earlier, but this, like, for some reason they feel the need to emphasize it, that we operate on latent variables, meaning hidden variables, the ones that are not exposed to the outside world, so to speak. So in ChatGPT, every token matters. Every token, every intermediate step is part of the full output, right? But here we denoise it, or noise it. Then like all the intermediate values are not important to us. We only care about the output. So we have a latent variable models of the form, this form that we already know, and this is a distribution of generated images, and it's crucial because we want to maximize this. That's how we'll train the model. We want to maximize the probability of generating these specific x0s coming from our data set. So later, down here, this will be our loss, because we will have to maximize the probability of generating these concrete images, where x1 to x capital T are latents of the same dimensionality as the data x0 distributed according to Q of x0. I was so confused by it when I first read it. So like this. So these are our latents of the same dimensionality, okay? But they don't have to be. In later improvements, like in next years from publishing this paper, one of the improvements that Stable Diffusion made is that they compress the latents. So they could operate much faster on much higher resolutions, because they took the image, they compress it, they operate on latents that are much smaller dimensionality, so they have faster processes. But for now, it began with latents of the same dimensionality as the data. And when I first read this sentence, if this sentence ended here, everything would be clear. That latents are the same dimensionality as the data. Okay, that's clear. But then they wrote this, that this is the data. Data is x zeros distributed according to q of x0. And I explained it to you already, but I was so confused that how x0 comes from q distribution, like our data set is just our data set, but it's just like math notation quirk, right? That this is just our data set. Okay, that's fine. The joint distribution p theta of x0 to capital T, I wrote it as capital T to 0 because it goes in reverse. That's the order it goes in, but it's fine. It's called the reverse diffusion. Don't call it reverse process, please. It's reverse diffusion, and it is defined as a Markov chain with layered Gaussian transitions starting at p of xt. So this is our starting point of reverse diffusion that doesn't depend on theta, right? Which is a normal distribution with 0 mean and I variance. And now we know these equations already, where each slightly less noisy image is produced by our model. So our model produces the mean and the variance, at least in theory. Also, I'm amazed by the fact that they first described the reverse diffusion and then the forward diffusion. Like, instead of building your mental model that we take a clean image from the dataset, we noise it, then we learn to denoise it. That's the order that things are happening. Why do they reverse it? It's fine. What distinguishes diffusion models from other types of latent variable models is that the approximate posterior, denoted like this, called forward diffusion, is fixed to a Markov chain that gradually adds Gaussian noise to the data according to a variance schedule beta 1 to beta capital T that we know about. Right, these are our equations. We slightly scale down the mean every time and we add a little bit of noise. Now my favorite part. Training is performed by optimizing the usual variational bound on negative log likelihood. The usual, right? Everything should be clear by now, so we can go further. No, we stop. Let's think about this. So this is the variational bound. It's the usual variational bound. So they explained nothing, almost. They explained that this is our true loss. So we want to maximize, well, let me do it like this. So we want to maximize the probability of producing our x zeros. So we want to maximize this and we minimize the loss because we minus it. So the convention is to minimize the loss function. That's why they write it like this. And we cannot compute it truly. So we estimate it with variational bound that has this form. And then this form. And this is our loss. That's how it feels to read those papers. Like, we optimize this, so we use the usual variational bound. This, we transform it into this, that's our loss. Let's move on. But no, like, can we stop for a moment? So I derived it for you. I derived it. I really did derive it, which is quite an accomplishment. I'm really proud because nobody could explain it to me. Everyone I checked was skipping very crucial steps, which is just like even papers skip so many steps. Is just I was ripping my hair out trying to understand it, and I eventually did, which is kind of amazing. But I'm surprised that nobody could really explain it to me. Like, that was amazing. I really watched all videos about this paper on YouTube, and everyone was skipping something. My goodness. All right. Just as a reminder, we are here. So they showed that they'll be optimizing the model with this variational bound that came from absolutely nowhere. This is our true loss, and they use the usual variational bound, right? The usual. So we start from this. This is our true loss that we showed earlier. Can you see it? It's just this one. We want to increase the probability of our model producing these images from our data set. And we just log it for better numerical stability, and we negate it because the convention is that we minimize the loss. So this is our loss, our true loss. This is where we begin. So I wrote it here. This is our true loss, and this loss is equal to itself. That's obvious, okay. But the trick with variational bound is that we introduce additional term. That has a known sign, like KL divergence here. This has known sign. This is always non-negative. So we introduce additional term that maybe will help us calculate it. Maybe will help us kind of like simplify it and derive some simpler equations. And all this is at the cost of introducing an inequality. But as you can see, because this is non-negative, this is always higher than the true loss. So this is like an upper bound. That's why it's called the bound. Like some people also call it the evidence lower bound. But in this case, when we get negated, it's the upper bound. It has various names, but what matters is that this is an upper bound on our loss, on our true loss that we don't know about and we cannot calculate. But in case if we can calculate this and we optimize for it, like we treat this as a loss and we push this down, our true loss will also go down because we lower its upper bound. Right? I hope that's clear. So that's how we end up here. And then, if you don't know what KL divergence is, because I, for example, use this in my Dreamer, so I knew that KL divergence is a measure of like the difference between distributions. Just you measure like a score of how similar distributions are. So that's how much I knew earlier, but for this video I had to actually look up the definition because we'll be diving into math. So this is our definition here. I could make a whole video about it. I watched videos about it even. So it's really a big topic and it's important. It's fun to know and it's useful to know where it came from, why it works, and so on and so on. But this is the definition, that KL divergence between some distributions, let's say P and Q, that's how we denote it. It's this integral over the entire space where we multiply a log ratio of these distributions. And remember that this is our reference distribution because this operation is not symmetric. So this is our reference and we calculate how much this differs from this scaled by the probability of our distribution. Okay, we will not be diving why it is and how it is, but this is the definition. Okay, and there's also like I will introduce the term right away. The expectance, because this will be also crucial. The expected value of something. Before you look at the equation, look at me. The expected value of something is very intuitive if you think about it. For example, if you have a normal coin toss where if it's heads you win $2 and if it's tails you win $1. Let's say it's fair coin toss. So heads is $2. That's how you write it. No, you put S here. Whatever. And then tails is $1. So how we calculated the expected value from playing this game is we multiply probabilities by their outcomes and we sum them up. So it's 50% times 2 plus 50% times 1. $1.50. Okay, that's the expected value from playing this game. Before I knew the definition exactly, I was thinking of it as the average, but kind of like a weighted average by the probabilities. So how much, like, yeah, it's just average. So how much do we expect to gain or lose from playing this game in the long run? Like on average, in the long term, right? So equal probability events like here is just average. This is just the average of these two outcomes, right? But that's the most simplified case. So we can make a more complex game and have, 10%, 10% of winning 10, and then 90% of losing 1, and that will be not 0, but 0.1, which is still not bad. Okay, stuff like this. So this is expected value in like the simplest form. And what we'll be dealing with here is just the same thing, kind of like, because we have integral. So if we had discrete outcomes, that would be just a sum, just a sigma, right? But, delete it. But because we're dealing with like discrete, continuous values, we have integral here. So we just sum up probability of each event with the value of the function, with like the outcome. That's it. That's just expected value. And as you can see, these two, let me take a laser, these two, they're not equal. I don't know why they put equal sign, but they are like connected. They are similar. So we have this and this, and if we treat this as our function, then we can easily transition between KL divergence and expected value. That's kind of important. So you can even, like, I was looking up like this, I think this comes from Wikipedia, that you can literally express KL divergence in terms of expected value. And sometimes, to make it even clearer, like here we note it as expected value of f function, but to make it explicit, we sometimes can write that this is expected value under this distribution, under distribution P. So that's what I wrote here, that KL divergence between Q and P, where P is the reference in this case. And this is exactly equal the expected probability of this function, of this log ratio, under Q distribution. Oh yeah, I wrote it here. It's like average. It's like weighted. Okay, I cannot write. Doesn't matter. So I hope that's somewhat clear. And now we're coming back to our equation here, where I simply rewrote the KL divergence term in terms of expected value of this distribution, of this log ratio, okay? And maybe you've noticed one thing, that this is our forward diffusion that produces all latent variables given x0, and our p-Taylor distribution that also produces all latent variables given x0, okay? I know it's counterintuitive. I know it doesn't really make sense at a first glance, but we've long broke our ties with the physical world, and we're diving deep into the world of mathematics. And this is just a mathematical construct, because any joint distribution can be just reversed. Kind of like, okay, this is our actual forward diffusion. Like, we are given denoised image and we noise them further. That's what we produce. But what this says is that given a specific denoised image, what could have been the probabilities of states we could have been in along the way? like given that we ended up here, what paths could we have taken? Okay, that's much simpler. But, like, if it's hard for you to understand, no worries, because it's hard for everyone. All right. So we rewrote this term in terms of expected value. Next, what we do is, because this is expectation under the forward process, and this has no connection to the forward process. This is just like independent of the forward process, because this is completely different distribution. This is the reverse process. So in terms of this is treated like a scalar, and we can just put it like here in here. So we put this here, right? This stays the same. Okay, I mean, the lines I write here make no sense, but it's fine. I'm going to lose it. All right, but this is. Oh my goodness. But this is getting more interesting. But now it's getting more interesting, right? Where's my laser? Oh, it's here. And now it's getting more interesting because we're splitting this thing into these two terms. How? Let me introduce you to conditional probability. This is conditional probability equation. That the probability of a hypothesis being true given an evidence that we've observed is equal to the probability of hypothesis and evidence being true divided by the evidence being true, like the probability of evidence being true. Okay, so applying this to our distribution here, we can treat this as evidence and we can treat this as hypothesis. So we, like here, we combine these two terms, so x0 and all the rest, divided by the probability of seeing x0. So this is exactly what we've done here, just flipped, because this is flipped. Okay, so that's that. And then maybe you remember the properties of logarithms from school. But if we have, if we subtract one logarithm from another, we can just put them under one log, while addition becomes multiplication. So subtraction becomes division. So we put this term here, and these two cancel out, right? So we're left with this. So this is our simplified form for now. And this form is written in the paper, like we want to get there. And so we can easily see the path forward because we can use simple properties of logarithms to get there. For example, put the whole thing under double minus 1 power. And we use 1 minus to flip them, and 1 minus goes here. These are just properties of logarithms, right? So we have this, and as you can see, these two terms are our forward and reverse diffusion. This is exactly it. I even colored them for you. This is exactly this and this. So we have exactly this, and we plug in the definitions. And this next form is written in the paper already. So what they did is they took out this term into its own logarithm, and they changed the product within the logarithm to sum of logarithms. And this is exactly the definition of our loss from the paper. And remember to not look down there for now. Like, this was the easy part. You know, I was bragging about deriving the equations. Like, this is fine. This was easy. This was shown on the internet. But the hard stuff will come. It's fine. For now, we're coming back to the paper. So for now, the training is performed by optimizing the usual variational bound on negative log likelihood. And we know where it came from. Everything's chill. We go further. The forward process variances beta t can be learned by reparametrization or held constant as hyperparameters. And expressiveness of the reverse process is ensured in part by the choice of Gaussian conditionals in the reverse diffusion, because both processes have the same functional form when beta t are small. This is what they mentioned in the introduction, that when the betas are small, when the noise added is very small, then they have the same functional form. A notable property of the forward process is that it admits sampling xt at an arbitrary time step t in closed form, using the notation alpha t defined as 1 minus beta t and alpha bar t defined as the product of all alphas up to this point. So we have this. They give us this. So this is a preparation for the training, because we will not be training on whole sequences, we'll be training on random time steps. But to get to a time step, we'll also be like randomly sampling images from our dataset. So to get a random time step, we would have to perform sometimes many noising steps. So what they're saying here is that we can go from any original image to any arbitrarily noised version of this image in a single time step, which is nice. And we can do it with this equation. But there's like a question, right? That pops into my head regarding this equation, because I'm very nosy. So where does this equation come from? Let's derive it. And that's how we learn about the reparameterization trick. Because this is a trick used widely in machine learning, where we take a random operation that is non-differentiable. Like in machine learning, we have to backpropagate the gradients back through the model, and we cannot backpropagate through random sampling. So this is a mathematical operation, sampling some z from some normal distribution of mean and variance like this. And the trick is, I mean, we can study the derivations, where the trick comes from and everything, but I'll just give you the answer that we can rephrase the random sampling operation in terms of just a simple function of mean, standard deviation, and the noise, which looks like this. Mean plus standard deviation times the noise. And thanks to this trick, our gradients can flow through the mean, and we separate our noise, which is kind of like the noise will not influence or mess up our gradients to the mean. And it will also backpropagate to the standard deviation, right? But it'll be more messy. That's how I understand it, at least. All right, but now we can use this trick to rewrite our forward diffusion transition that's defined like this, where like this thing is the mean and this thing is our variance. So we rewrite it like this. And in the paper, they wrote the equation in terms of alphas already, right? So we use this here as well. We redefine, like we rewrite all the terms with beta in terms of alpha. So we have this nicely reparameterized equation, and we can plug values into it. Like I will not do it generically in some like abstract x of t. I will just like see what happens step by step. Okay, so let me scroll here. X0 is given to us. This is our starting point. But then to calculate x1, we can use this equation. So x1 will be slightly scaled down version of our previous image plus a little bit of noise. And then x2 is exactly the same thing with all indexes up 1. Okay, that's fine. But now we can plug in our calculated x1 into here, which I did here. Okay, this is just the same equation but written like this. And then we expand the equation to group all coefficients with corresponding variables, like here. I noticed that this should be longer because this original image is also a part of our mean, so that's fine. And I forgot to mention that when we combine Gaussians, we get another Gaussian. And the rules are, for this specific form here, is that we add the means and we add variances. But remember that these terms that we're getting here are standard deviations. So when we square these terms, they will add nicely to our new variance. So we square them, just getting rid of the square root. We expand, multiply, simplify, and we get this form. And looking at our final mean and variance, we can observe some pattern. I mean, you could prove it using, general terms, xt, but I just want to show you like the general principle, the concrete example. You can check it for yourself that if you calculated x3, you would get here the final mean as like with alpha 3 here and 1 minus alpha 3 here multiplied by everything else. So this is how we get the pattern that they included in the equation. So we get this series right here as mean with this and variance like this. And if we denote this long product under the square root as alpha bar of t, then we get this final equation from the paper. So now we know where this came from and we can go further. But I also need a break, so be right back. Efficient training is therefore possible by optimizing random terms of L with stochastic gradient descent. That's what I said earlier, that what we calculated so far and what we're calculating constantly is the whole loss, right? From the whole process. But in practice, we'll be selecting random time steps from this whole process and optimizing on that, on batches of data, right? That's how we do it in practice. We never train on the whole data set ever. So this is what we're doing. And further improvements come from variance reduction by rewriting L from equation 3. So this is what we got here as this. Right. But this time we have appendix A that includes the details of the derivation. How nice of them. How nice. And let me tell you something. This appendix is quite an appendix. It's an appendix and a half. Let's look at it. Extended derivations. I'll be kind of jumping a lot between this and my own derivations because I was trying to study this. I was trying to understand exactly how did they get this final form. And I consider this one of my proudest moments here, that I actually figured it out more or less, right? Like the best I could. To the best of my knowledge, like nobody showed it like this, so I'm really happy. But yeah, let's trace it step by step because of course they explain nothing and they make big jumps. And my favorite jump is the last jump, like from this form to this with like zero explanation was like a cherry on top, because everyone, like nobody could explain it to me, and even if they explained it, they said something like, then we will write the log ratio in terms of KL divergence, which is like, you cannot just convert to log to KL divergence because that doesn't fulfill the definition. I was like, why cannot explain it to me? Is this how science is done? We just like assume it's fine and we move on and we make so many shortcuts. I don't know. I'm not sure, but I will explain everything, so don't worry. And we begin pretty much with this second form because this is where we ended up with the previous loss, right? This is the same thing. So what they did here is they took out the case where t equals 1 from this sum and they put it here as a separate term. I don't like this notation because like the change is very subtle here. So we were starting with 1 up to t, but now we'll be starting with 2 to t, and we have this separate term, okay? I think that's fair. Now, notice what's happening. They split this term into these 3 terms, which is a big jump. And this is my second favorite jump here, because where does x0 even come from everywhere, even though it's not included here, right? And like, you cannot just like rearrange stuff with conditional probability. So we had to investigate. So let me introduce you to Bayes' theorem. There's a lot of depth behind Bayes' theorem, like whole approaches, whole techniques, whole algorithms have been created based on this equation, and there's so much significance behind it. Like it's a way, it's like a foundation, like it's kind of like a foundation for the whole branch of statistics, the whole approach. There's like frequentists and Bayesians, probably. I don't know, but this equation is a way of updating your previous beliefs given new evidence. Yep, there are frequentists and Bayesians. Okay, like, this is a big topic. Unfortunately, we cannot dive deep into Bayes' theorem in this video, but hopefully some of you will get interested and explore by themselves. And that's at least my hope for giving you this context and the background for our understanding. But for now, we only need just the equation, the Bayes' theorem equation. So probability of hypothesis being true given evidence equals the probability of evidence being true given the hypothesis, so we reverse the order, times probability of hypothesis being true. This is called prior. This is our prior belief about hypothesis being true before we saw the evidence. Stuff like this, because Bayes' theorem has a really, profound connection to real world and real events. So, and that's that. And this term divided by probability of evidence being true. And using Bayes' theorem on this term here that we wanted to expand, right? We expand this term. We use Bayes' theorem and we expand it into, like, this is evidence, right? This is hypothesis. So we switch the order here, times hypothesis being true divided by probability of evidence being true. Okay, and when you look at this form and you look at what we want to get, this, I rewrote them and the three terms from the equation. Like, this is what we're doing, trying to tell if these things are equal. Because if you look at the terms, the form is very similar. Like, you have exactly the same terms here, but to every term you have this x0 as given, right? So what is going on here? Where does the x0 come from? And it took me a while, but this is very fascinating. So this is our forward diffusion transition, and to every transition we can just give x0 in our case. Why? Because our process, our diffusion is Markovian. So it doesn't care about the past. We can just give it past and it changes nothing. So this equality holds because it's a Markovian property. That's why modeling the process as a Markov chain is so useful. So we can just do that. And I can imagine that pretty much, like when we have this term here already, we can, like, to every term we can just add x0, because why not? But I wanted to properly and derive it in more detail, so I did it here. I got it here. I was super happy that I finally figured it out. So to figure out how we go from this, because like we know this equality, and now from this I want to just obtain this exact form. Okay, so I rewrote this here, and to derive this final form I need to introduce you to chain rule of probability. Okay, like, we're really learning stuff today. We're not just learning diffusion models. We're actually, like, to understand all this stuff I had to learn a ton of probability and math overall. So there's the chain rule of probability, And the main point of it is that a joint probability can be broken down into conditional probability times the probability of the condition. Okay, that's it. But to illustrate it, we have probability of A and B happening at the same time. And thanks to this rule, we can just rewrite it as probability of A happening given that B is true times the probability that B is true. And because joint probability is symmetric, you can also write it like this, that B given A times probability of A being true, okay? And the same holds for more variables. So probability of A, B, and C being true equals probability of A being true given B times C times probability of B and C being true. And we can break this down even further and split it like in this case here. And we can rearrange it however we want. So probability of A, B, and C being true is also the probability of B being true given A and C times probability of A and C being true, and so on and so on. Okay, this is chain rule of probability. Now I rewrote this for clarity. So I assume this is A, B, and C, right? And I rewrote it like this. And we want to prove this to get our final form. So what I do first is I rewrite this with the chain rule. So I just kind of rearrange the equation a little. It's kind of like this variant, but I solve for this. So I put this under this, right? I just rearrange it. And I already observe that we have, similar forms here, similar letters, so to speak. So here we have given A and C. So I will take out A and C from this and rewrite it with the chain rule. And this already is very similar to what we want to get. But somehow this is given C and given C, while we have and C here. But with the chain rule, we can immediately simply just take it out, right? And they will cancel out. And we got our final form. So we proved this. We proved this. And notice also that this is our forward diffusion transition, but this is like our true posterior transition. So it's our reverse diffusion coming from the forward diffusion process. So this is the mathematical construct I was talking about, that it's not how it happens in practice, but we're just kind of like playing with the distributions. And here I also wrote that like the reverse process coming from the forward process would be intractable even, but because of this conditioning on x0, it is computable. And it all stems from this process being Markovian. So we're coming back to our equations. We've proved this. We know where it all came from. Now, for the next step, we split this sum into two sums. Okay, that's nothing complicated. And now we notice what's happening with this sum. Because when we expand it, when we expand the sum, kind of like as products under the logarithm, we observe that we have telescoping series. Because after expansion, we notice that these terms cancel out. This term with this with next, and next, and next, until we have these two terms left only. Do you see it? That we have very similar terms here, but here is t and here's t minus 1. We start from t equals 2. So here we have 2, 1, 3, 2. So they will all cancel out. So we're left with this simple term here. And now we notice that these two terms can be combined together and these terms will cancel out. So we're left with this from these two terms, right? And now they start to group similar terms. Because if we look at this term here we have x of t, of capital T, and here we also have x of capital T. So they just group alike terms together. They put this term here, okay? We're left with this. And for this jump here, they use the minuses, they use the map to switch nominators and denominators here, right? So we have pluses here, plus and plus. And here things started to get a little tricky because this is our final jump to make. Like we're so close to the final answer, but it took me so long, my goodness. I kind of regret not recording myself struggling with this because that could be an interesting time lapse, but my goodness, that was not easy. Because let's come back to the paper. So we have obtained this form successfully. We are even one step ahead because here they have clear divergence between Q with respect to P. And for that, Q would have to be at the top. So I already switched the orders, okay? And now we only need to convert the forms to KL divergence. But oh my goodness, it's not intuitive. Like, how do you even do it? I checked so many sources. I watched a video of a guy who explained everything so well, but he didn't explain everything. And for this jump, he literally said, as I mentioned earlier, that we just rewrite this log in terms of KL divergence. Like, it's as if it was so obvious to everyone in the industry except me that nobody explains it. It's just like, there's no need to say it. It's trivial. So I'll explain it. In case there is someone among you who doesn't immediately see the obvious, how logarithm can be just rewritten as KL divergence without fulfilling its definition. When in doubt in research, get nosy. So let's investigate this because this is unbelievable. So my problem with this transition here comes from this definition because, I mean, the definition is fine. It shows a nice connection between KL divergence and expectation under some distribution and log ratio, of log ratio of two distributions, okay? That's fine. The relation is fine and it's nice. But my problem with this transition is that, yes, we can transition this log ratio under the expectation into KL divergence. That's fine. But in this transition, the expectation is not being used up. It looks like this is exactly how they wrote it in the paper, that expectation under Q equals expectation under Q here and this term, which tells you, which kind of indicates that this is exactly the same thing. But the key to solving all this is that it's not the same. What they meant here is exactly this. I just rewrote the same thing, but wrote the explicit expectation that we are under the forward process. And also our data set. It's kind of confusing right as I'm recording this. I noticed that here, oops, don't look down. Well, my goodness, that here I wrote it like this, but earlier, when I was explaining you, I wrote it like this. I'm not that sure, but I think this should be from 0 to t, because we're calculating loss under the forward process. That's what they wrote, expectation under Q. So I just plugged in the definition of the forward diffusion, right? This is it. That given x0, we have all the latents, and this is our forward diffusion, and that's what we calculate the loss with respect to. But the true loss doesn't come from one process. It comes from every process, starting at every image in our dataset. To be clear, that's not what happens in practice. We're calculating the true loss, the mathematical construct, right? In practice, we sample not even all data, all time steps. We sample specific time steps from just a few images. for like practical convenience and for efficiency of training. But ideally, mathematically, we would take our whole data set, fully noise it, and then like fully denoise it, calculate every time step with our model, and then calculate the loss. That'll be our one gradient step, which is terribly slow, but you know, that's how it works. So I have a hypothesis that is unconfirmed because nobody did it like this, but what I should have done to make my later derivations work and to make it work in my brain logically, that I should have wrapped the scale divergence into an expectation over our whole data set. Like this. Then it would all work perfectly with layer derivations. But I'm not entirely sure. I mean, I cannot really be certain when I'm doing science by myself here, but if someone more experienced and knowledgeable than me in the topic could comment on this, I'll be grateful, because I don't know if that's fully correct, but it looks like it is. So we're coming back to where we left off, where I rewrote our equation with the explicit expectation. Okay. So we take this expectation and then we split this expectation into two due to a law of total expectation. I believe this equation just comes straight from Wikipedia's page on expectation, like expected value, but it also results, like we also know this from our chain rule of probability, that we can just split it and take out this x0. And now it makes logical and mathematical sense, right? We calculate first the loss, the full loss of our process, and then we calculate the expected loss over our processes with respect to all of our data set. And now it makes sense, my goodness. So what we do, we split this into three terms, right? We can just distribute the expectation. And now this becomes our scale divergence. That's fine. Also this. And this term remains because there is no forward diffusion here. Like with respect to this probability, this is just a scalar. So that's what we're left with. The full loss, and this is the compact form, right? This is just expectation under Q. That's what they wrote in the paper. And also as a bonus, I tried to be more precise with all these calculations and simplify it even more. And like this expectation from earlier becomes only this because we marginalize over all latent variables except the ones that matter, like here. But I wasn't like fully sure about correctness of all this, so I just put it aside. So just remember that we can even simplify it further and make the distribution only from the terms that matter for us for this expectation, stuff like this. But I didn't like fully commit to it. I don't know what's happening. Anyway, I feel like we should really move on, so let's do it. That was our appendix A. Thank you for the appendix. So we finished here and now we know where it came from. Very nice. So equation 5 uses scale divergence to directly compare reverse diffusion against forward diffusion posteriors, which are tractable when conditioned on x0. That's what I said earlier, that this true reverse diffusion could not be calculated if not this condition here, because of the Markov property. And they tell us that this true reverse diffusion transition has a form of this Gaussian with this mean and this variance. Very nice. But there's one particular question that always comes to mind. So this is the true reverse process, okay? Let's do it. We split it using our chain rule of probability. Perfection. We split it further, okay? And now we notice one thing. I mean, also we need to get rid of, where's my pen? we need to get rid of this to have our form that we are familiar with. And we get this, where each of these terms is just forward diffusion that we are familiar with. Like this is just jumping, this is just singular transition from t minus 1 to t. This is going from x0 to xt minus 1, and we have this equation. And this is just x0 to xt. We also have this equation. And we plug them in. This is our single transition in the forward diffusion. This is our transition from x0 to xt minus 1. And this is from x0 to xt. And we have three Gaussians that we have to combine. I didn't do it manually this time. I really had to save time. But if you look at the rules of combining Gaussians and stuff like this, that's how we get all these equations. That's how we get this form that they showed in the paper. So at least it's nice to know where it all came from. And while we're at it, because I remembered one thing, that I had one nice version here, because here was the derivation of the skip forward diffusion that skips multiple steps, and I made this diagram as well. So like it's important for you to remember to keep this in mind, to have this like mental model that previously we had this forward and reverse diffusion, and now after some exploration we know that we can go normally. Yeah, that's fine, but we also have this equation that can skip to any xt from x0. And now we know that we have these skip equations that we plug in the values, the equation, we combine the Gaussians, we get this. All right. So this is what they showed here. Consequently, all KL divergences in equation 5 are comparisons between Gaussians, so they can be calculated in a Rao-Blackwellized fashion with closed form expressions instead of high variance Monte Carlo estimates. Okay, whatever they say here, they just mean that calculating KL divergence between two Gaussians is much simpler, easier, better than if we were dealing with any complex distributions. Okay, that's fine. Now, the next section. Diffusion models might appear to be a restricted class of latent variable models, but they allow a large number of degrees of freedom in implementation. Alright, one must choose the variances, beta t, of the forward diffusion and the model architecture and Gaussian distribution parameterization of the reverse diffusion. To guide our choices, we establish a new explicit connection between diffusion models and denoising score matching that leads to a simplified weighted variational bound objective for diffusion models. You'll see. Ultimately, our model design is justified by simplicity and empirical results. I love this. This is like a beautiful way to say that we just tried stuff and some worked, some didn't, so we just picked what worked and it's justified by practice. Our discussion is categorized by the terms of equation 5. So these three terms. Because this is the loss of the last time step in the reverse diffusion. This is from the first, and this is from all the middle time steps. This is a great part. Forward process and L capital T. We ignore the fact that the forward process variances beta t are learnable by reparametrization and instead fix them to constants. Thus, in our implementation, the approximate posterior Q has no learnable parameters, so L capital T is a constant during training and can be ignored. Okay, so this is funny because look at this term. This term is our loss from the last time step. But what it says is that the endpoint of forward diffusion match the starting point of reverse diffusion. And it's not so obvious that this is true because the schedule can be learned. We set it constant, we set it manually, and we kind of like it's up to us to pick a correct schedule that will make this true. But because we don't learn it, it doesn't even depend on our parameters, on our neural network. So this is a scalar either way, so we can ignore this and throw it out. But if we were learning the schedule, this would be important. So this is funny because they made us struggle. We had to derive all these complex equations. They try to be fully mathematically correct. And then at the end, we just like, for practical aspects, we just simplify everything. And we're like, yeah, okay, actually, we don't need this. So that's that. Then reverse process and L1 to T minus 1. Okay. Now we discuss our choices in a reverse diffusion transition defined like this for these time steps. First, we set the covariance matrix to be equal to variances I, so on the diagonal, to untrained time-dependent constants. So now they say that despite that they were telling us constantly that this covariance matrix is learned by the model, they're like, actually we'll set it constant, we'll also not learn it. So experimentally, like this is, I love this section. Experimentally, both variances equal to beta t and variance is equal to this complex beta tilde that comes from the true reverse diffusion, like this. That was like, that's here. Yes, that's it. Had similar results. So they tried both of these variants and they had similar results. The first choice is optimal for x0 distributed according to pure noise. Like reading this as a beginner was entertaining, to say the least. And the second is optimal for x0 deterministically set to 1 point. I mean, let's keep reading. These are the two extreme choices corresponding to upper and lower bounds on reverse diffusion entropy for data with coordinate-wise unit variance. My goodness. I mean, I was reading this and it's unthinkable how they play with the minds of beginners. I was reading this, I was like, what is going on? What do you mean x0 distributed according to a noise? Like our, our data set is the furthest thing from noise. Okay, but they mean completely something else. This sentence kind of explains everything because these are two choices, two variance choices that are optimal for either maximum entropy dataset and minimum entropy dataset. And maximum is when dataset is just noise, then this variance is optimal. And when our dataset has the lowest entropy, this variance would be optimal. Okay? And the true dataset, in practice, the datasets we will be using will be somewhere in between these two scenarios. So I believe for this paper, they picked this just right away. But when I was analyzing further advancements and when I was writing my code and investigating it and how people do it in practice, people also, like in the future, after this paper came out, they proposed that the model learns the interpolation between these two cases, meaning that the model would like figure out what is optimal and how much entropy there is in our data set. So it would like self-tune this parameter. And I've also seen cases where they picked one of those, let's say this, for training, and then after training the model for inference, they got better quality if they, like after training, they switched the variances to these. But after training, not for training, right? Which doesn't really, like, I cannot connect the dots in my head. Like, how can you train it one way and then change the parameters and it works better? And why? And what is going on? I don't know, okay? We don't really have to understand it right now. They picked this for now. Second, to represent the mean mu theta, we propose a specific parameterization motivated by the following analysis of LT. And I am reading all that because I derived it myself. So welcome. This is our loss. We threw this out the window already. This we will throw out the window in the future. And now we're analyzing this middle term. So, this is our target. This is our true reverse diffusion transition coming from the forward diffusion distribution. I love this. So this is our target. This is the optimal case. If we knew everything in the world, that would be optimal. And this is us, because I empathize with neural networks. So this is us. This is target. Like this is the guy she tells you not to worry about. This is us, where we just have mu and sigma from the neural network. I mean, okay, actually the next step is just throwing this out the window and just putting the optimal variance here. So this is us for now. We have our variances. We don't know the mean. And how about, this is a question for you, how about we train the neural network to predict this mean, just straight up? I mean, it's not like it's wrong. It's suboptimal, but it should work to a degree. But because we can do better, because we know that this is the form of our optimal solution, and at any time step, like during the process, we will have xt available. We will not have x0 available, but all this comes from our schedule. These are just coefficients. These are like constants that, I mean, coefficients that we can just look up. We have these available. So it's suboptimal to learn all this when we know most terms. We can just predict this, for example. So I rewrote it like this, and this is us for now. And what do you think? Can we predict this? Is that a good idea? And the answer is yes. It's a totally valid idea. Actually, somewhere in the paper they write that they could just predict x0 and be done for the day, and that's fine. It's a totally valid idea. But in their early experiments, they found out that predicting noise performs better. I mean, the model performs better when it predicts noise, but this idea could work as well, and it works pretty much. But if they want us to predict noise, we'll do it. We'll derive it. So what we do? We write out the equation from forward diffusion that connects x0 and xt. This is this Gaussian that we rewrite using a reparameterization trick. And we solve for x0. So now we have x0 that we put into this equation, right? So this is the new form of our true reverse process coming from the forward distribution, and that only depends on xt here and here and noise, and variance is constant. So let's focus on the mean. So I rewrote this optimal mu tilde mean here by splitting this term into this and this, right? I split it here and here. Then I transform it. I want to group. I group all the terms with xt and epsilon. Now here I make use of this property that comes from just definitions of alpha bar. We have something like this, so we can collapse these two terms. So I collapse them, these two terms. These are these two terms exactly, and these two terms exactly. So the top term disappears, and on the bottom we'll have only square root of alpha t here and here. Okay. The next step is I collapse kind of this into this, because it's the same thing, just square root. So we have square root left here. And here what I did is I took out the common terms here before the parentheses, and I took out these terms before the parentheses, kind of like pretending that this was without the square root. Like I multiply this by alpha t, so it's all preserved. I took this out, and I have alpha t here without the square root, right? I hope everything's clear. Then we evaluate this parenthesis, and beta t is just 1 minus alpha t. Alpha t times 1 is just alpha t, And alpha t times minus alpha bar t minus 1 is just minus alpha bar t, right? So that evaluates to this because this cancels out. And this term is the same one as this term. So like this parenthesis and this term cancel out. That's perfect. Then we go further and we have exactly the same here. This term preserved and xt with this only here, right? And then we take out this common term here to get our final mean. So this is our new form of the mean of the true reverse diffusion, right? This is still our just normal reverse diffusion. And then we evaluate this loss that comes from all the middle terms. So this is the scale divergence between these two distributions. I wrote them right here. And this simple form only applies for Gaussians that have the same exact variance, which we do. I mean, we kind of chose it to be this way for simplicity. So this is the term where we have just this coefficient and a squared difference of the two means. And so we plug in our calculated area means. And this is just our mean from the neural network. Now, do we train the neural network to predict this mean? The answer is no, because we have these coefficients here. We don't have to spend our model's capacity to predict them when we know them. Also, we know xt. So we assume our predicted mean to have this form right here, because we have all that we need except the noise. This is the true noise. This will be the predicted noise. So we simplify the equation, we take out the coefficients, and we have this, which matches our paper. Like this is what they derive in this section that we were analyzing. So do we train the neural network to predict this noise that will have to match our true noise to minimize our loss? What do you think? The answer is yes, but with some nuance. I'll get to it in a second because like pretty much we were analyzing this section in the paper and they were deriving all this stuff, and this is what we have. Well, why is it so big? This is what we have here, and this is just xt as an argument to our neural network. I don't know why they write it explicitly like this, but these are just arguments. It doesn't matter. So like we predict noise to match the real noise with these coefficients. This is what we derived, okay? And they brag here that it resembles Langevin dynamics and the denoising score matching somewhere, stuff like this. So, the denoising score matching here and Langevin-like reverse process and Langevin dynamics. All right, to summarize, we can train the reverse process mean function approximator mu theta to predict mu tilde t, or by modifying its parameterization, we can train it to predict the noise, epsilon. There's also the possibility of predicting x0, but we found this to lead to worse sample quality early in our experiments. This is what I mentioned. We have shown that the epsilon prediction parameterization both resembles Langevin dynamics and simplifies the diffusion model's variational bound to an objective that resembles the denoising score matching. Nonetheless, it is just another parameterization of our reverse diffusion transition, so we verify its effectiveness in section 4 in an ablation where we compare predicting noise against predicting the mean, the optimal mean, mu tilde. That's fine. That's fine for now. I mean, I kind of want to skip this section because they always do funny thing, right? Like they write all these equations, full derivations, so complicated. We have this coefficient here, and then they eventually, like, after we skip one section, they write, however, we found it beneficial to sample quality and simpler to implement to train on the following variant of the variational bound. And this is just exactly the same thing, just without the coefficients. Like, without this. This is just funny. Like, someone wrote in the comments that it looked like they just came up with this, and it worked, and they came up with all this math to justify it. But no, I mean, it actually makes sense because, like, even if this is the true loss, let's say, like still we minimize it by just matching the real noise, and this is just kind of like obstructing our way or like skewing our numerical values and stuff like this. So it makes sense to me that we can just drop it because like whatever happens, we have to just match the noise anyway, and it's fine. But okay, we'll read it in a second. But then I will show you in my slide that I wrote that this is the ultimate loss. This is how we will train the model in practice, and in code we will just calculate the mean squared difference between our predicted noise and the real noise, and that's a loss. That's everything after all these derivations. And as a summary, I have my final diagram here, and to like sum up everything that we've done. We have forward diffusion and reverse diffusion. And for both cases, we can just go step by step because we can. For forward diffusion, we can skip multiple steps at once and get any xt that we desire. That's fine. And also with the forward diffusion distribution, while knowing x0 and xt, we can derive the true reverse process, xt minus 1, if we want. Later on, I mean, in the future papers, you'll see that we will be able to skip also the reverse diffusion, but that's not a topic for today, okay? This is our final diagram. I'm happy. This is how it looks. This is what we've learned and derived ourselves. Now we're coming back to the paper because we have also the L0 to analyze, which is, oh my goodness, that's a nice topic. So they say that we might need to calculate L0, which is the log probability of producing exactly the original image. And they give us like a ready recipe for calculating the log probability. So because our neural network outputs continuous values between -1 and 1, and our pixel values can have 256 values that are discrete, I mean, assuming grayscale, right? So they split this output range into 256 bins. Then they calculate the upper and lower bounds of the specific bin we fall into with our image, and then we integrate on this interval and we sum this up to get the real probability, right? Because like the general idea is just that we have continuous distribution and we have to integrate on the interval because our output image is discrete, right? But ultimately at the end of sampling they display predicted mean noiselessly. So just raw output and that's it. They don't implement any of this. Fine. It's me again, the more knowledgeable future me in a hoodie. So yes, they don't implement the decoder. They describe it, they don't do any of this. But then they write that they display the raw mean noiselessly at the very end of our reverse diffusion. And that means something as entirely that, I mean, you'd have to look at the sampling process, but the sampling is like this. You denoise it one time step at a time, and then you add a little bit of noise. That's the Langevin dynamics part. Don't worry, I'll describe it later. But the thing is that our model produces only the means. So we have means of our Gaussians for every pixel, for every dimension we have, but we add a little bit of noise, which makes it a proper sample of the Gaussian, right? This is the reparameterization trick that we know the mean, but then we add a little bit of noise to make it a sample from this Gaussian. And that's what we do for the whole reverse process, except the last time step. That's what they're saying here, that for the last time step, we don't make it a proper sample from the Gaussian, we just display the means noiselessly. That's what they mean. And you'll see it in the sampling algorithm that we add noise every time except the last time step. That's what they meant here. They kind of like mixing multiple topics, but It's fine. We also need to talk about these algorithms, but that in a second, because I want to finish, let's say, this section. So the simplified chaining objective. This is when they mentioned this, but let's read it. With the reverse process and the decoder defined above, the variational bound consisting of terms derived from equations 12 and 13. Yeah, this and this, because they ignored the L capital T, so we have only these two, right? Is clearly differentiable with respect to theta and is ready to be employed for training. However, we found beneficial to sample quality and is simpler to implement to train on the following variant of the variational bound. So this is what I mentioned. So not only they dropped, they dropped this whole thing, but they also dropped, of course, the coefficients here. And that's what they train on. Fine. Where t is uniform between 1 and capital T, the t equals 1 case corresponds to L0 with the integral in the discrete decoder definition approximated by the Gaussian probability density function times the bin width ignoring variance 1 and edge effects. The t greater than 1 cases correspond to an unweighted version of equation 12, which is this, of course, analogous to the loss weighting used by the NCSN denoising score matching model. Fine. L capital T does not appear because the forward process variances beta T are fixed. Yes. Algorithm 1 displays the complete training procedure with this simplified objective. We'll take a look at it in a second. Since our simplified objective discards the weighting in equation 12, it is a weighted variational bound that emphasizes different aspects of reconstruction compared to the standard variational bound. In particular, our diffusion process setup in section 4 causes the simplified objective to downweigh loss terms corresponding to small t. These terms train the network to denoise data with very small amounts of noise, so it is beneficial to downweigh them so that the network can focus on more difficult denoising tasks at larger t terms. We will see in our experiments that this reweighing leads to better sample quality. But actually, forget the whole thing here, because what the industry did is they just came up with a new, better schedule, because how quickly they add noise here in this implementation in this paper is suboptimal. So they came up with something else that I also implemented in the code, so you'll see. So this is not that important, but the rest is fine. And we have these two algorithms here that you'll be seeing in the code. This is just like, this already an introduction to the code, that this is what they're doing in training. The training is like this. Repeatedly in a loop, sample from our dataset, pick a random time step, sample noise, and train on our loss. So this is how we calculate, this is just xt. So from this we calculate xt, we feed this xt and t to our network that predicts the noise. We have the real noise that was added, and that's our loss, and train this until you're satisfied. And for sampling, we pick our starting point as pure noise, then we loop through each time step and we denoise it bit by bit. But to do that, we pick a little bit of noise, we calculate the optimal mean of our slightly more denoised image. So this is this exactly. But here we add a little bit of noise. We didn't talk fully about yet because it didn't show up in the equations. This is the Langevin dynamics that I mentioned earlier. That here, this is what we do here, is we follow the gradients that we've learned of our image space. But to make it a proper sample from the distribution, we have to add a little bit of noise according to our schedule. It's complicated to explain, but I also watched a great video that explained why this is necessary. Because for now, what our model does is it's kind of denoising the image. Wow. right? But it really denoises it in like the guy called it the logical part, that we start from something and we want to get some structure from it, but we have no way of creating detail. We can only like remove noise, make it smoother, make it more structurally appropriate, but we cannot add details. And this added noise becomes like our material to work with. So maybe you know about subtractive manufacturing, right? Like we start from material and then we subtract it. We like CNC machining, like milling, right? We have a block of material, then we remove material to create what we want. And there's also additive manufacturing, like 3D printing. We start from nothing, just a base, and then we add material in the ways that we want to create something that we want to. And this is like a combination that our diffusion model can only remove the detail, so to speak. It can remove the noise. It can decrease the entropy. That's a good way to put it. It can only decrease entropy. And the noising part is as important as the noising. Like they cooperate together. We have the logical part, and so we start with the block of material. Our neural network removes a lot of it, and then we add a little bit of noise to add some texture roughness, some details here. We remove more, add a little bit. Remove more, add a little bit. And it's like a cooperative process to make a fully functional product. I mean, the image.
See, the diffusion model is trained to remove noise from images that we artificially added noise to, not to add details to a painting that lacks them. So the diffusion model isn't creative enough to know that it ever needs to add some details. And the noise term isn't smart enough to know what kinds of smudges or details depict a meaningful pattern. It's easy to think that the diffusion model is the one doing the heavy lifting, since it's the one that takes a lot of resources to train, and which has to understand the structure of the probability distribution. While the noise term doesn't have to do any of that, and we get it for free. But I find this perspective helps me viscerally realize that the noise term is just as important as the diffusion model in obtaining high quality or high probability images.
And that's pretty much it. Then they show the experiments. They show why it resembles progressive coding and lossy compression and stuff like this. But I didn't have much more energy and time to analyze this paper. I'm satisfied with this, but there are also like many future papers that came after this that improved on this architecture, that are fascinating, that really showed incredible stuff. So this paper served us well, but it's time to move on to the code now. I'll show you my code where you'll see code that is even simpler than what they implemented here. Then you'll see code that matches their architecture more or less in a simple way. And then you'll see improvements that came in later years. So I'm kind of happy. I mean, I didn't implement everything, right? I didn't match the advanced neural networks and the newest advancements, but we'll still learn a lot. I woke up 2 hours ago. In 2 hours, I'm leaving in a train to my family city, to my family home for Christmas. So like it's all done last minute. Throughout this night, I was running my last experiment to show you on this video, and the training is not even done. Like it's like I will not show the full capability of this repo, but it's good enough. We have to be happy with what we have. So this is my code, right? This is last comment 40 minutes ago. Clean one-file implementations of core diffusion ideas at increasing complexity, from ConvNet to attention unit with additions. I'm really proud of this repo. I like the idea behind it. Pretty much, I don't have to say anything because, link needed. I'm recording this video right now. But pretty much everything is explained pretty well here. Like I really worked on this with me. So this is our final result of my best code. So the MNIST dataset of handwritten digits is pretty much solved, and CFAR10 dataset is pretty decent. I believe it could be solved. I mean, it's not ideal. The images are not ideal, but I didn't tweak the parameters. I just run it for longer on default settings that are very small and that are adjusted to this dataset. So if you increase the sizes, maybe depths, the batch size, lower the learning rate, stuff like this, I believe this could be solved. I mean, it's explained everything here, that this is 400 epochs, and I could train it for 1,000. It was still like, look at this run. This is exactly this run, and the loss is still falling. Like, this is much smaller than even this, right? So like, this is not saturated. I could train it for longer. I just didn't have more time, but it's good enough, right? And I will not be describing you here how to run it, what are the parameters and everything. Everything is described here, but I want to tell you about the idea behind the repo, because I wanted to do it like this. So these are not like individual comments. I didn't save the history of my code here. These are like multiple parallel versions. This is like the most simplified version of the repo. It's self-contained. It's just one file. You just run this one file and it works. So for this version, I didn't even inject the time step. So the neural network didn't know what stage of reverse diffusion we're in, how noisy the image is. So this is the first version. Then I give it the time step as a float. Then we do proper time steps as it's done in like modern models with sinusoidal embeddings. Then we have unit, attention unit. Then we improve the schedule, we improve the initialization, upsampling, smoother weights. So if you're trying to understand everything, the last version will be probably like too complex of a start. But if you start here and understand what we're doing step by step, I think it's super simple, super clean, and very approachable. Here I describe every change, what changed and reasoning behind the change. So for example, this version 8 is fixing this problem explained here, the checkerboard pattern. I don't know if you see it. Stuff like this. So it's all well documented. Use it, read it, learn it, right? And when you're watching it in the future, I believe like there's still a lot of things to be done. I think I'm gonna keep improving this. I mean, not like immediately, maybe some simple stuff like here I wrote that it would be nice if I could save the checkpoints and outputs, not every epoch, but every certain amount of epochs, because I have like here, I have like, oh, it's here. I have like, you know, a ton of outputs, and even though I don't need all of them, but for now it's fine, okay, it's fine. This might vary, but the idea behind the repo stays the same, right? So this will have maybe more versions, maybe slightly different versions. Maybe I should like kind of trim it down, and like this version is not that big of a step up, so I could just implement it somewhere else. We'll see about the details, but what I want to go through in this video is this first version, just to like give you a rough idea, just as a good starting point, right? Actually, I'll show you locally. So this is our entry point with parsing all the parameters. So you run the scripts pretty much from the console only. You don't just do this, because then it will start training, but it will not save any outputs or checkpoints or nothing. So I run it like this, like, whoops, what happened here? I run my last experiment like this. This is the 400 epochs, saving outputs, saving checkpoints. This is the name of the run and dataset. This is this run that produced this. So you run it from the console, you pass the parameters, and we run the main function. And the main function is just checking the dataset, because we have to take a different dataset. It downloads the dataset if it's missing. We transform it to normalize the ranges that we want. We check the image shape to pass it to our model here. Here we instantiate the model. We also print all the parameters of the run and the name and the dataset, so you're less likely to make a mistake. Like here, we run like here, starting run, training on MNIST dataset with an image shape of 12828, right? And if you provided a checkpoint, it will try to load it. Then we have our main training loop, and this is pretty much like a universalized interface to train these models. So there's nothing really custom here. We just call update method on our diffusion model, and it diffuses, like it returns a loss that we just print, and we save these outputs. So we sample from the model, and then we save checkpoints if you wanted to after every epoch, and we just train and train and train. So like this main loop is the same pretty much for every version of my script, and I wrote it in a README that the previous checkpoints are getting deleted. So we only keep only the newest checkpoint. We don't have a list of checkpoints like with the outputs here. But if you don't want that behavior, you just adjust it, right? You take the checkpoints there, current path, copy this, diffusion model, save here, delete all these, and this works totally fine. And for the model itself, we have a noise predictor, which is just a bunch of convolutional nets with activations and batch norms. That's super simple, super basic, and it works kind of not that well, right? But it's like as simple as it can be. And then our main model is like this. Some parameters, optimizer, I keep the level here. I mean, this is just like, how many epochs we've trained it on, but I named it level because I want to start slowly introducing gaming vocab, meaning that level is just experience, amount of experience, right? So if some model with lower level beats higher levels, the higher levels are super lame. Even though like this is not a perfect metric here because I increase it at every epoch, while epoch kind of like the amount of training loops we've run on each epoch varies by batch size. So this is not perfect for now. I mean, I'll have to rethink it, but pretty much, yeah, if you lower the batch size, you have many more training iterations on one epoch. So the epoch means like it gives you more kind of, but your training is less stable. It's hard to judge, but whatever. Here, this is our whole schedule, right? Here I expose as, I register these as buffers. So we want to keep this schedule as part of the model, easily accessible to the model, but not everything is needed here. Like we don't need beta directly. So we need betas to calculate further stuff, but we don't need betas exposed to our model like for the math. Like, we don't use it directly. So yeah, this is just our schedule, and we don't operate directly as in the equations in the paper. We don't operate directly on alphas and minuses and divisions because, the schedule is constant. We can just pre-compute every factor, every coefficient, every like division, and just use it for faster training. But I'll show you. So this is our sampling algorithm, and we pre-compute this. This is what I call here the noising step scale factor, right? We have 1 over square root of alpha t, and this is alpha square root reciprocal. That's how I call it. This is here. So I just pre-compute all the coefficients, and we use them directly. So this is exactly these two algorithms. So for training, we pass a batch of images. We select time step, random time step from our range for every image in our batch. Then we calculate the noise that exactly matches the meshes of our batch. Then we calculate all the noisy versions of images according to these time steps, right? This is our equation with alpha bars. This is our equation to just like skip many noising steps. That's that. Then we predict the noise added with our noise predictor. That's why it's called like this, because it predicts noise. Then we calculate the mean squared difference of our noise prediction and the actual noise added. That's our loss. We optimize it, we return it. Voila, this is perfection. Look how aligned everything is. Beautiful. Super simple, easy to study, easy to work with, but it doesn't perform that well. Wait, let me see, let me find it. Oh yeah, this is the result of our version 1. Not bad. I mean, it's trying something. without even having the time step. It's all just convolutional layers that don't have they have local coherence, they don't have global coherence. Only later we introduce a unit with residual connections that make this much better. And for example, let me see version 3, did I run it? So this is the version that is aware of time. So it's the same architecture, but they have information about the time. It's kind of less messy, it looks more like the digits, but it's still not great. And this is with the unit. So, alright, this looks pretty good. There's some noise. I mean, my current version 4 is slightly upgraded, so this is not the real version, it's slightly outdated, but it's still pretty good. It should still be fairly similar to my current version. And then it's just, I mean, I didn't make full runs, I didn't test 7 and 8 and stuff like this. I just have my final version. And this is the final version. I mean, this is how these digits just look like. Some are thicker, some are thinner. That's how it is. And that's it. The code will slightly change, but it's pretty much it. So read it, study it, run it, do whatever you want with it. And enjoy. That's the crucial part. We're here to have fun. And thanks for watching for that long. I mean, I did not expect this video to be that long, but it's not really my fault that I want to teach you about line-driven dynamics and Bayes theorem and chain rule of probability and autoregression, GANs and and everything, and show you the code and paper. But that's how I am. Okay. I mean, I need to rethink my whole approach to YouTube. I think I'll have some fun. I'll experiment with different kinds of videos. But for now, this is it, and I need to go and catch my train. So thanks for watching, and see ya.